Okay, cool. Hello, everyone. I'm very excited to see all of you. So it's Chen Hao from PingCAP. I'll be the online host today, and Li Shen will be the on-site host. So today we'll be talking about TiDB's table partition and data definition language, aka DDL. We have two awesome speakers today, Mattias and Cong. So Mattias is currently a senior database engineer at PingCAP. Prior to joining PingCAP, Mattias worked for Booking.com, where he spent a significant amount of time on MySQL. Before Booking.com, Mattias spent more than 15 years at MySQL, where he worked on the MySQL server team and focused on the partitioning storage engine. So let's welcome Mattias. Mattias?
Thank you. Yeah, I started at MySQL 2007, I think it was, and then I left 2015. So I was there for more than 7 years. And I mostly worked with the partitioning storage engine even before it was released in MySQL 5.1. The last thing I did before leaving was to implement and push the DB native partitioning. But today is more about the table partitioning in TiDB that I start to be more and more familiar with and helping with. We will first I will just discuss a bit about TiDB, how that works and how it actually distributes data, then what table partitioning is, and what the use cases for table partitioning in TiDB is. Because the use cases in TiDB may be slightly different from MySQL or other databases. So first, just a bit about what is a table. It's just a structured file, more or less, with the data in it. And the simplest way is just to have a heap-based table or a non-clustered table, where you more or less generate a row ID, or in some databases you have an offset instead. We just store the data row by row. And to have some kind of control over the data and so on, you normally have a primary key to ensure that you only have the same row once. You can also have a secondary key, so they would look just the same as a primary key. In the end, it will point to the row ID or the offset. Something that's more popular since long, it's actually clustering together with the index, which means that instead of just pushing over the data rows directly to a file or storage, you store it together with in the index, so in the leaf of the index, or in the data files in the case of TiDB, where we have an LSM tree instead of a B tree. The secondary index works in a similar way, but instead of having an offset into the data, it completes the full pointer with the rest of the primary key columns if it's not already part of the secondary. To get a bit of a view how this would work in TiDB, first just a very short architecture note about TiDB. It's 3 different node types. I would start with the stateless SQL layer, which is very easy to scale for the compute, and it handles the client connections, it does the parsing, it has the optimizer, etc. And then it uses TiKV storage, so it's a distributed key value storage engine, which distributes the data and uses a raft for synchronizing and achieving HA and balancing. A bit of the balancing is done by the placement driver, who has the metadata about everything in the different schemas. And a bit about the regions. TiDB splits all tables, indexes everything into data regions around 100 megabytes. That's how it tries to balance. And it can also split or merge these data regions depending on load or size. And there's someone a bit of background noise. Let's see if we can fix that. It's based on range completely. So We normally add the table ID and the row as a prefix for all of it. Or if we have index data, then we use an index prefix instead as well. So doing in this big range that are spread over all the TiDB nodes, the range is actually starting with the table ID. So if you drop a table ID, for example, you have a big range that you can delete instead of going into each and every key. So a bit about what partitioning is then. It's a horizontal table partitioning we are speaking about. You can also say that there exists a virtual partitioning, which more often is referred to column store. That's something we also do with the TiFlash, but that's nothing I will go much into depth here. There are several ways to organize or to split the data in horizontal partitioning. There are four main types. It's hash, which is just have a modulus over an int column or a function that generates an int, for example, 2 days or some date functions. Range, which can take an integer column or even a string or a date. That's easy when you're, for example, have a data that is connected to a date or a timelines. So it's easy to have a more hot data concentrated or also delete or drop really old data that needs to be purged. One of the reasons why that's heavily used is instead of having a big transaction or a batch of transactions, this is actually DDL type of operations. Actually, Cong will talk a bit more about DDL specifics later on. But that means that the resource usage for actually doing these drops or truncates partition is much more efficient than involving transactions for each and every single row. The traditional partition use cases, it's managing large set of data. For example, if we would look at MySQL, if you have a really big table, so you have a lot of the disk space, and you're limited by memory, then the whole index wouldn't fit into memory for the whole table. So that's when partitioning was used to actually speed up insertion and so on, because normally you'd need to go through the whole index. And if that's not in memory, then you're starting to be IO bound just for using the index. That particular issue does not exist in TiDB, but normally it's about managing large data sets. There's also performance. One big gain is, as I mentioned, you can drop or truncate a partition. It's very efficient. So you can reclaim data with a simple command. In TiDB, there's actually some safety network, so even if you delete the data, it won't be removed from disk immediately. There will be a garbage collector that will do the big range delete and drop the files after a configurable amount of time. The second use case for increasing performance is data pruning or partition pruning, which means that the optimizer can see at the query and the conditions which partition that would match these conditions and only use that part of the table. So instead of doing a full table scan, you can maybe scan a small set of partitions. This is something that's also beneficial in TiDB, especially when one is using TiFlash. Since TiFlash is a column store, it does not use any indexes, and it's great if you're doing a bigger aggregation or a big reporting queries, for example, or any kind of analytics. A normal case for partitioning is to increase parallelism. In TiDB, that's a non-issue because even non-partition tables run concurrently in the cluster. In MySQL, it's actually a single thread regardless of partitioning or not. You can use this since you know more about the data, use more IO splitting, avoid hotspots, for example. That's something that TiDB also has other solutions for. You can use auto-random, for example, for non-partitions tables as well. You can use more logical split of data. You can even do a geo-partitioning. So if you would have a cluster that spans several regions, you can specify which partitions should actually be stored in which regions. Something that you need to be aware of is how to use secondary key lookups, because normally they will go, you will store the secondary indexes within each and every partition. So it's easy to drop the whole range of secondary indexes together with the data. That's something you need to test if you're running something with a lot of the secondary keys. And all this is more or less down to how you slice and dice the data. So if you know your data well, and you know the business logic behind, then you can leverage that data and organize your tables with partitioning in a more fitting way. It's not the silver bullet in any way, but there are use cases where you can use partitioning to tweak up the performance quite a lot. As I mentioned, be a bit aware about indexes, secondary indexes. There are different ways to handle even the primary key. MySQL and TiDB uses the primary key within each and every partition, which adds a limitation that all partitioning columns must be included in all unique indexes, so we can ensure the uniqueness of the index. We are using something that's called local index, so each secondary index is grouped together with the data within the partition. There is also something more generic called a global index, which would be an index over all the data in the whole table. So you would only partition the data, but not partition the secondary index, which has its use cases, but it also means that it loses the benefit of dropping a whole partition, because then you still need to go in and clear out the data in the global index. It's something we actually have done some work in already, but it's not fully supported yet. And there's nothing in MySQL for that either. Here's a picture of the key visualizer where you have some hotspots. So this is just a 2D space. You have time in one axis and the different ranges in another. And there can be hotspots both in read and in write. Very common, it happens in write because you're maybe having an out increment, or you're storing per time or something like that. So it will be concentrated to single data region whenever you do this. And you have the similar thing when you do reading, that you can be focused on. So that's something you can use, for example, hash partitioning to split out, or use auto-random, for example. The biggest limitations for partitioning is, I would say, that you need to have all these partition expression columns within all unique indexes to ensure there's no duplicated keys. So within MySQL, which we inherited the design from overall, you will be limited if you have one ID that you're using as a primary key, but you would like to partition on something else. Then you have a bit of dilemma if you want to extend the primary key, or maybe not using partitioning at all. There's some limited set of functions that are supported for the partitioning expression, and not all of those are optimized for partitioning pruning in the optimizer either, and it's similar in MySQL. The good thing is that TiDB also is already distributing all the data for a single table in a range-based setup, as I showed before. So there are ways to achieve some of this even without partitioning. The maximum number of partitions is 8,000. It's the same limitations in MySQL. one big change is that all the DDL, all the partitioning management in TiDB is online. There's no such thing as blocking DDL in MySQL. That's something that Cong will talk a lot more about and go deeper into in his talk soon. So let's go and see a bit more about the different partitioning types. One of the most common is range partitioning, as I said. You have a create table, you partition by range, or you can also partition by range columns. Without the columns keyword, it's limited to integers. With columns, you can also use date, time, or strings, for example. Otherwise, you need to have a function that would map to an. This is super good for deleting old data or to concentrate more time-relevant data in its own partition. You can do quite a lot of partitioning management for that. You can add partitions, you can drop partitions. We are currently working on the implementation for reorganized partition, which will be completely online. In MySQL, it's blocking. You can truncate a partition. You can also exchange partition with a non-partition table, which is great if you want to export data, remove data from a partition table, but archive it somewhere else, for example. Or if you want to take in data into a partition table, you might want to check the data integrity, you might want to normalize data or something like that. You can do that in a separate table, and when the data is ready, you can exchange it in partition, so it's very fast. It's just a metadata change for moving data in or out in a partition table. Something that is new in TiDB and that's not supported in MySQL is partition by range interval. So instead of listing each and every partition, you can just say that I want one partition per interval, and you say how big the interval is, and the first partition should start somewhere and the last partition should end somewhere. So instead here of writing and create table with 100 rows, that would just state all the different partitions. You can efficiently do this. It's a synthetic sugar, so it's as stable as anything else, but it will generate 100 partitions. It also simplifies the partition management by just setting a new end range, for example. Here, instead of adding 100 named partitions, you can use all the table last partition less than. Here it would just extend with 100 more partitions. And likewise, you can remove the first partitions by setting which interval the first partition should start at. In this case, it would drop 4 partitions. The main use cases is size and pruning. Size matters, but in TiDB it matters less because of its distributed nature. There might be other use cases where it's really interesting in doing TiDB as well, so that's why we have implemented it. Pruning effect scanning, so the less partitions that are matching the query, so the conditions, the less data will be scanned. Especially if you're having something that needs a scanning operation or doing a lot of aggregations, for example, this is very useful. The drop partition is super efficient. There's no transaction overhead. It's more or less maps to the single file system command and some cleanup in the metadata. So not a heavy load on the system at all to do. You can also use explicit partition selection. So if you know the name of the partition, you can just say that I want to use only this partition or this set of partitions, which is also good for a safety net. If you're doing update or deletes, you know that even if you're missing out with some condition, it will still be limited to this partition. List partition is another use case. instead of having per range, you're enumerating each and every value and put those values in the specific partitions that you defined. Likewise, here you can do a list columns, or just list. List would only be for integer columns, and list columns would also support date, time, and strings. You can more or less use a list with functions as well to achieve per month or anything like that as well. Here is actually one example from OSS Insight. That's a site we're running that takes in all events from GitHub. I think currently it's somewhere just above 5.2 billion events. And the main database table, the GitHub events table, that is actually partitioned by list. And here you can see that it takes all the different values of column type and maps it to its own partition. It's the same here with list partition. You can add, you can drop, you can reorganize partition. Well, we're working on the reorganized partition. You can truncate partition, you can exchange partition. Use cases are a slightly bit different because normally you don't use list partition for dropping all the data. It can be that you're using it per status, for example, and then you can clear out status. But it can also be used for constraining a column, a bit similar to how enum works, which also makes it quite useful for reporting on the specific types, for example, for that column. It also supports the explicit partitioning selection. Let's see what the time is. Okay. More or less on time, I think. The hash partition is one of the very simplest ways. It uses an int-based modulus operation, and it's just distributing that over the number of partitions that you define, which is super easy to use for spreading out load for different data regions if you have hotspots, for example. It's less useful if you have range queries, for example, because then it will touch all the partitions and it may have a bit of overhead due to that. It also has some management functions. Currently, just as a reorganized partition, we are not supporting changing the number of partitions for hash-based yet, but you still can do the truncate partition and exchange partition. And the use cases is mostly doing distributed load and avoid hotspots. So you have known control over your data. For example, if you know that you have 10 different IDs that are just rotating, you can use this, for example. You can also use it for round-robin distribution. For example, you define 16 different partitions, and you fill them up, and then you truncated partition afterwards. So it just goes in a loop, a bit like you're a ring. Something we recently added is geo-partitioning, which is the placement rules in SQL. That also goes down to partition level. So by that you can use it for partitioning, for placing the data either in locality per region, for example, in the cloud, or specific data storage types. If you have the machines that are using SSDs and some machines that are using more long-term, cheaper storage, then you can actually specify which partition should go where. We added this support for columns partitioning and the interval partition that I mentioned, and a lot of minor improvements as well last year. What's coming next is the reorganized partition that we are currently working, that will allow both for hash, list, and range partitioning. It will also allow alter between a non-partition to a partition table and remove partitioning from a partition table. We're considering doing a default list partition We are looking into how we can break the limitation for all unique indexes must contain all partitioning columns. Maybe we'll complete the global index. Maybe we will solve it in other ways. Since I have you here, if there's any other feature requests or questions, please raise your voice now, because it's really interesting for us to know a bit what you would like to use partitioning. Which is my very last slide, and whatever you do have for questions technically or for the future or anything, please just reach out in the chat or just unmute yourself.
Yep. Okay. Thanks, Mattias. So I do have a question online for you. So I'll just read it. Can you please provide an example of the table partitioning? Can it be configured by using one or more columns using the different methods such as hash, range, list, and key?
Yeah, so the easiest way is probably going back to here. For example, you have a quite big example for partition by columns. So here is actually the full create table statement in our site OSS Insight, and you can see there's a lot of different columns, a lot of different keys, and in the end it will say it's partitioned by list and list the different values in the type columns. Currently, we do not support combination of the different ones like sub-partitioning or anything like that. Were there
cool.
questions?
When you partition the data like that, what happens to the raw data? That the raw data will still be living on the what you call the PD nodes, and only the keys, like the indexes, are the ones that are getting actually partitioned?
No, so internally you can more or less see partition as a table. So internally it looks like it has its own table ID, but logically it's a single table, which means that it will reorganize the data into these partitions. So instead of having a big range for the whole table, it will have multiple range for each and every partition.
Okay. But then isn't it behaving, because I see that like all of these are columns of the same table. That means that like push events and create events being two separate columns, they're being treated as two subtables within the.
No, so if you read the create table syntax, so here is what it's specified to partition on, and it will partition on the column type. So that's a type. Okay. Well, that's a column.
Yes, a column.
Okay. And the values in that columns are push events, create events, and so on. And each of those types, each of those values in the column type will have its own partition.
Okay, I was confused because it sounded like you were doing something columnar, but that's not what it is. Okay.
No, so yeah, it's a bit confusing, but since it's a real world example, I think that's a more correct to discuss around.
Yes. No, that makes a lot of sense. Thank you.
Cool, Mattias.
Yes.
Yeah. There is a couple of following up questions on the previous one. So would you please explain the online operations for partitions? For example, can you submit only DML on the partition table?
We support DDL as well. I think Cong will discuss a bit more about that in a generic term, but that applies to partition tables as well. So from the user perspective, a partition table should not be any different from any other normal non-partition table. And I saw also a question about sub-partitions. That's nothing we support right now. But if you have a good use case, that's something that we will take up with the PMs and change the priority for as well.
Yep. Okay, cool. Thanks, Mattias.
Yeah, and I will stop sharing.
Yep. Okay, cool. Secondly, Cong will be talking about TiDB's data definition language, which is DDL. So Cong has worked on distributed database system for more than 10 years. and contributed to TiDB project for more than 4 years. As a maintainer of TiDB, he mainly focuses on the cluster's computation layer, which is the TiDB server. It includes authentication, security-related features, metadata management, and character sets. Let's now welcome Cong.
Yeah. Hello, everyone. My name is Cong. I will continue from Mattias' introduction to the partitions of TiDB. And since the DDL part of partition is quite important, and also the DDLs or the metadata management is a key part of the TiDB as a distributed system, I would like to continue the topic with the data definition language or DDL in TiDB. So yeah, nice to meet you. And I am a tech leader of the TiDB team from PingCAP. I usually focus on the parser part and the connection part, also as well as the management, metadata management of TiDB. So before we started, I would like to introduce my opinion about the challenges of the TiDB of the DDL in TiDB. I think there are 3 major challenges for the DDL in TiDB. They are inherited from the TiDB system as a distributed database. The first one is a strong consistency. So consistency is quite important to our system. So whenever you run a DDL job or the metadata schema change, or we need to always guarantee that the data or the data and the metadata will be always consistent. And the second one is the horizontal scalability. Since we might have a lot of records, billion of rows in TiDB. So when we have the metadata change, a very large amount of data during the change. So a fast or online fashioned schema change will be very important to our system. And the third one is MySQL compatibility. We aim to be compatible with MySQL. So the DDLs in TiDB should be I mean, the DDLs from SQL standard and the MySQL dialects should be supported by our system. So the agenda of my topic will be basically into 5 parts. Firstly, I will introduce the basic concepts of DDLs in TiDB, and then I will try to introduce the online schema change algorithm. What is the challenging part and how do we solve it? And thirdly, I will try to introduce the implementations of DDLs, different DDLs in TiDB. And I will have the overview of MySQL compatibilities and then some roadmaps of our system. So firstly, the basic concepts. So the first concept is about the schema versions. Since the TiDB system, it uses a MVCC model, which means that all the data has is a timestamp or with a version. So as for the schema version, the schemas in TiDB, let's assume that initially we for example take the create table as an example. Let's assume that initially we have 2 tables and we have the schema with those 2 tables, and the schema version is 0, and then we have a create table statement, and the TiDB will generate a DDL job for it, and then we will generate the table's definition or the table info in our system. And this table info will be persisted in the storage layer and then applied to all the TiDB servers. So we have the newer schema version, or schema version 1 in this case, which has 3 tables, including our the the newly created table. This is how the schema and the schema version works for a TiDB cluster. Then, so yeah, all the schemas in TiDB are with versions, and every time we have a DDL job, and when the job is finished, all the TiDB servers will try to update the schema version to the latest one. However, due to the nature of a distributed system, it is impossible to make sure that all TiDB servers updates the schema version at exactly the same time. So, but we can guarantee that we have at most 2 consecutive schema versions exist in a TiDB cluster, because we introduce a lease mechanism so that all the TiDB servers hold a schema that is valid as long as in a lease of time, in the lease time. So when lease expires, all the TiDB servers must reload the schema or update the schema. And then if a TiDB server is not able to renew the lease, it refuses to work, so that we can guarantee that at most 2 schema versions coexist in a TiDB cluster. So this is about the schema versions and the lease. And the part 2 is about the online schema change algorithm. So online schema change means that when we have the DDL running in the cluster, we always allow that the concurrent DML, the data manipulation languages, will be always permitted. For example, we have in this example, we have the create index on a specific table in session 1. And for session 2, during the execution time of this DDL, we have a session 2 manipulating the data on the same table. For example, insert, update, delete, so that those operations will not be blocked. However, this is not a simple. This is making this work is not so simple. Let's take an example. So remember that we might have 2 different versions coexist in the same cluster. So for example, we might have TiDB server A with a older schema version, which is we have the table definition without the index. And we might have another TiDB server with a newer schema version with the table definition with index. And now we have seen that we have the insert statement applies on the TiDB server B. And since that in the TiDB server B, we have the index definition, it means that this insert statement will apply 2 new records to the storage layer, which is the row record and the index record. And then we assume that we have a delete operation on the same record we just inserted. But therefore, TiDB server A, there's no index definition on the schema, and then it does not know that there is an index record with the same row. So this is when the data inconsistency happens. Now we have the standard index. So this is the problem we are trying to solve. And in order to solve that, we divided the whole process of create index into smaller steps. This is something like that. We introduced some intermediate state, and during those intermediate state, we know that the TiDB server A here, we know that okay, there's it's kind of like the hidden index definition, and when it delete the record, it knows that, okay, that there will be a related index with this record. So the index record will be deleted as well, so that we guarantee that the data will be always consistency with each other. And okay, I will talk more about the implementations of DDLs in TiDB. So basically, there are three DDL algorithms in MySQL, and for TiDB, we basically have two DDL algorithms. The first types of the first algorithm is that those DDLs with only metadata modification is needed, which is faster, and it is similar to the instant algorithm in MySQL. And the second one is those DDLs need update both data and metadata in a table. It takes a longer time and similar to the in-place algorithm in MySQL. What we are trying to do is we try to make more DDLs in TiDB to the first type of using the first algorithm, which is faster, or we only need to modify the update the metadata.
And all the DDLs we're doing, is that blocking or are they online?
I will make sure that all the DDLs will be online. Yes, so that for example, for the copy algorithm in MySQL, it is usually a blocking algorithm, so that it's a when apply it will blocks the related DMLs, which is we treat as unacceptable in TiDB. Yeah. So for example, the add columns, because the major data in TiDB storage layer is a row-based one. So all columns of the record is encoded together, which means that basically, if you want to add a new column to your table, it requires an update for all the existing rows. However, for the add column DDL in TiDB, we don't fill all the column data actually. Instead, we just modify the metadata. And when we read the actual data from the storage, if we found that the newly added columns, the data for newly added columns does not exist, we will try to fill it with the default value or none, depending on the column definitions that is newly added. And for the drop columns, we don't delete the column of data actually. Also, we just modify the metadata, so that, for example, when performing a read operation, the data of dropped columns are simply ignored. And when performing the update operation, we will have a row record that does not contain the dropped columns. And things are similar to drop or truncate table or partition or the index. Actually, we use a asynchronized bulk delete, which means that firstly we simply remove the schema object from the metadata, and then we write the range of records to be deleted into a kind of a GC range table, and those records, the range of those records will be removed when the GC happens. So and it can be done in a very fast or effective fashion, which is a delete range operation. So the fourth part is the MySQL compatibility. I will give an overview of all the DDLs we have supported, and we have implemented, and those DDLs that is on the road. So basically, most of the DDLs of MySQL has been supported by TiDB. For example, the create table, alter table, or the create database, and index, create index, alter index, as well as the partitions actually, which is you can treat it as a subcommand of the table definition, create table, alter table. And we are still working on some more DDL supports, like the foreign key, which is very important to TiDB users when they're trying to migrate their workloads on foreign keys to TiDB. And also we have some other DDL operations to be supported. And besides that, we have some extensions that is not supported by MySQL. For example, the sequences and the global temporary table, they're part of the SQL standard. And also we as Mattias introduced before, we supported the placement of policies that allows that you could define the rules of data placement on different partitions or different tables or different databases, so as you could have a better management of your data across different regions or racks or countries. And so the last part is the roadmap of DDLs in TiDB. So I think there's basically two major directions. The first one is developer friendly. So for example, we provide better compatibilities with MySQL. The foreign keys as example, and the more kinds of the partition related DDLs is another one. And we wanted to provide better management for the data in TiDB. For example, we might want to define the TTL, or we want to have the scheduled DDLs. You could trigger the DDL according to some scheduled time. And another major direction is the cost saving, or we provide a higher performance for some heavy DDLs, like the create index, modify columns. We want to better utilize the resource of the cluster to make it faster. Or we can we'll also imagine that on the cloud we can be a lot of the processes can be optimized. For example, we can be elastic to have more resources when we're doing some heavy DDLs, or we can better utilize the cloud resources. For example, we could think about the adopting the hotspot instance from AWS to deal with some background job of the DDL processing. Okay, also since TiDB is a open source project, all the developments are public on GitHub. Also, we welcome all the engineers to join us to contribute to TiDB. Yeah, you can join our channels or check our document, or we have the public weekly meeting, and all the process of the development will be introduced during that meeting. Or you can all join PingCAP, join us. So this link we will have the all the open positions. There's feel free to contact me directly. Yeah. So this is basically all the introduction from me. So yeah, I'm happy to answer any questions.
Okay, cool. Thanks a lot, Cong. So I'll have a question for you. So can we run to DDL at the same time? I mean, concurrently.
Oh, yes, I saw this question from the Zoom chat. I think Mattias has is a explicit answer for that. Yeah, we have the admin command. I think I can.
I think the question was, can you run several DDLs concurrently? Can you run them at the same time? Was that the question?
Yes.
You mean the also the different?
It was in the Q&A.
So yeah, if whether I can run 2 DDL at the same time. So after I issue a DDL and that one is still running, and then I issue another DDL, is that okay?
Yeah, actually, in before the release of 6.3, for firstly we have two kinds of let's get back to my slide.
First, we split between more metadata changes or reorganization changes and index changes. Yes. Because the index changes can be done concurrently and spread out, something that takes quite a long time normally.
Yeah, so since we have two types of DDLs, the metadata changes and they need those with both data and metadata changes. Actually, in the past, we have two job queues. You can imagine that we have two job queues for those two types of DDLs. And for the jobs in different queue of different types, they can be run concurrently. But if you have you have multiple jobs with the same type, they will be queued. For example, if you are adding index for one table and another, you want to have another add index job, so it must be queued or wait for the first job to be finished. But after TiDB 6.2, we have a the new DDM scheduling framework, which allows that all the DDL jobs could be run concurrently. So yeah, so the short answer is before the 6.2, they are limited to the job queues, and after the 6.2, the concurrent DDLs is possible. So without limitation.
Okay, cool. Thanks a lot, Tom. So I also have a questions online, which is not quite relevant to the topic today, but it's generally related to TiDB. So the question is the different performance QPS between native MySQL and TiDB is almost more than 50%. Is it expected due to TiDB have 3 topology like TiDB server, PD server, and TiKV? Maybe Mattias?
Yeah, so if you're running small point queries and the data is not that big, yes, then you would have everything in memory in a DB if you're running MySQL. So that would normally be very, very fast. As soon as you are actually using this distributed cluster, so it's more data that wouldn't fit into memory in a single instance, for example, or a bit more complex where you can leverage the parallelism in TiDB, then TiDB starts to scale much, much better. Well, basically, MySQL is limited by a single box, and you cannot scale writes or anything like that in MySQL more than using sharding, for example, which then limits the SQL usages and so on as well. So yes, for smaller instances and very small, simple queries, then MySQL most likely will be faster. The more you grow, the more complex queries you have, the better TiDB will be.
Okay, cool. Thanks, Mattias. Another question is DDL in TiDB transaction?
Transactional. Okay, I think you might answer is if we put multiple DDL jobs, DDL statement in a explicit transaction. For example, begin and create table and commit. Where this a transactional or possible in TiDB? So if so, the answer is no, because this because we aim to be compatible with MySQL, and the DDLs in MySQL is not transactional. If you have a explicit transaction like the begin, then you run a DDL. The transaction will be committed. The previous transaction will be committed automatically. This is what MySQL have done for the transactions and the DDLs, and it is the same for TiDB. We will have the previous transaction to be committed. It means that
internally the design internally is possible to extend this to be transactional also for DDLs, since we have different version and metadata and hidden states and so on. But no, currently we're aiming on being MySQL compatible. MySQL does not support that, so we do not support it.
Yep. Okay. Thank you. So, is there any questions on site in the meeting room?
I think there's another question about the estimated timeline for foreign keys, right? So
yes.
Yes. Okay. So we hope that it can be delivered in the first quarter, at the end of the first quarter of next year, which is the March of 2023. But this is not we cannot guarantee that, because foreign key is kind of a complicated or big feature, especially for a distributed system like TiDB. Yeah. So yeah, hopefully we could release it the next quarter, or in the first quarter of next year.
Okay. Cool. Yeah. Thanks, Tom. Okay. So we do have some gifts for the speakers today. Lishan, would you please take over?
Yeah. Okay. Yeah. Thanks for Cong and Mattias, the great talk. And we have a gift for the speaker. It's this is dedicated slide for the speakers in our meetup, and there's SQL statements on this photo. Yeah.
Thank you.
Thanks. Yeah.
Thank you.
So okay. Yeah. Yeah. To earn this fancy photo, you can submit a talk to our meetup as speaker. Yeah, we welcome any topics in the infrastructure or cloud native area. So yeah, thanks for coming.
And Tom, would you please let me share my screen so that I can show a couple of barcode.
I will stop my sharing, please.
Yeah. Okay. 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 Can you see my screen?
No, not yet.
Okay. It seems like there is some security limitation on my Mac. So maybe you can share that one. Let me send it to you on lock.
Okay.
Okay. I've sent you this the slides on lock.
So let me try to share it. I should.
Yep.
This one.
Yep. Okay. I've also granted you the permission. Yep, that's it. Cool. So if you would like to join Slacks on TiDB, scan first barcode, and we also have a linking page, and you can also try TiDB Cloud for free. Okay, cool. That's everything from this meetup. Thank you very much for coming. I will see you next time.
Try TiDB for Cloud for free. We just released it as a serverless as well. So that's before we had it as something we called a developer tier, but now we're actually having it as a proper serverless tier.
Yep. I think that's the first. Is that the first serverless product in the world? I mean the serverless distributed database. Yes. No. Yes.
Serverless HTAP database.
Yeah. Okay.
Yeah.
New contender, DB.
Okay, cool. Thank you very much. Thank you everyone for coming. I will see you next time.
See you. Bye bye.